So, in order to prove some of the fundamental results of set theory and begin to define other branches of mathematics based on it, we need to start with some axioms that we will religiously take to be true. There are many possible choices of axioms, but the most popular set is the ZFC system, or the Zermelo-Fraenkel system with the axiom of choice. And the first axiom that we'll take is that the universe is non-empty. And have typed these out directly. So that there'll be no confusion. So this is a logical statement that there exists a set Y such that for all X, X is not an element of Y for all sets X. And I want to note that we denote this set as a 0 with a line through it, or two brackets containing nothing. This is the empty set. So the set with no elements is called the empty set. And denoted as this or this. Axiom 2 is the extensionality axiom. And this axiom is saying for all X and for all Y, set X is equal to set Y if and only if for all sets Z, if Z is an element of X, if and only if Z is an element of Y. Two sets are equal if and only if they contain the same elements. And at this point, with even just these two axioms, we can actually start to prove certain results about sets. The first theorem is that the empty set is unique. What this means is that there's one and only one empty set. This proof is in the book, but I'm going to go through it here. It's a proof by contradiction. We'll start by assuming that the empty set is not unique. This means that there exists at least two sets X and X prime that are empty, and that X is not equal to X prime. by axiom 1 for any set Z. Z is not an element of X, and Z is not an element of X prime for any set Z. This is by the definition of an empty set. But by axiom 2, X has to equal X prime, which is a contradiction, and thus we've proven the empty set is unique. Now, the question you might be asking is, well, why is this true? Why does X have to equal X prime under these assumptions? And the answer is actually quite clever, and it relies fundamentally on the implication operator. The statement Z is an element of X is false. Because we know that X is the empty set. So this is by axiom 1. Therefore, the implication Z is an element of X, or if Z is an element of X, then Z is an element of X prime is true. By definition of the empty set for all Z. This is because if you have an implication statement, if P then Q, and P is false, then the implication is true. This is the Latin principle of ex falso quod lebe, and how we've defined the implication operator. And if you start from a false premise, the implication will always be true. Likewise, the statement Z is an element of X prime is false. So the statement if Z is an element of X prime, then Z is an element of X is also true. So we have the by implication that for all Z, Z is an element of X if and only if Z is an element of X prime. So therefore X has to equal X prime, which is a contradiction. Because we assume that X equals X prime, or X is not equal to X prime. and therefore we have to conclude that the empty set is unique. So this is a very, very neat proof and showing how to do a proof by contradiction using even the first two axioms of set theory. I want to note as well it also follows from Axiom 2 that we will term in the next in Axiom 4 actually, but I'll talk about it here, the unordered pair set if I have two sets x and y and I form the pair set, or the set of sets x comma y, is unique. In other words, order of listing of elements in a set does not matter. The set x comma y is the same thing as the set y comma x. And this will make a little bit more sense once we define what a pair set is and how to actually construct it. But we'll see a little bit later on in the lecture that we can form ordered pairs sets as well. We have a slightly different notation for these though. So let's continue to move on. The next axiom is Axiom 3. Which is called the regularity or foundation axiom. And this is the following statement. For every non-empty set x, there is some element y of x such that x and y have no elements in common. By the way, we say that two sets x and y are said to be disjoint if they have no elements in common. Now, this foundation axiom, we'll see, directly addresses one of the problems that we found with Russell's paradox and resolves this paradox for us. But Axiom 4, in order to keep moving on here, we're going to get over and do, at least at the beginning, two axioms at a time. Axiom 4 is the pair set axiom, which is a statement that if we have two sets x and y, we can form an unordered pair set M that contains exactly x and y. And we can write this new pair set as x comma y. But like I mentioned before, from Axiom 2, we can prove that this is the same thing as y comma x. The pair set doesn't care about order, and in general, sets don't care about the order. So to give you an example of relatively simple example of how we use the pair set axiom. If I have a set X, which is just for instance set 0, 1, 2, 3, and I have a set Y, where Y is a set A, B, C, the pair set is a set containing the sets X and Y. Or this set right here. And it's important to address that. We can write these in either order, just like the individual elements of the sets themselves can be written in any order that we want. It's still the same set. For sets, order doesn't matter. However, we will be able to define order a little bit later on and distinguish what it means to have an ordered set. It's like an additional structure on the set itself. But in general, from a set standpoint, sets are unordered collections. I also want to make a note here. It follows from Axiom 2 that if X is a set, then by Axiom 4 we have a set containing just X itself. Etc., etc., etc. Take the set containing the set containing the set containing X, and so on and so forth. And this theorem right here is one that really helps resolve Russell's paradox. Now that no set is an element of itself. To prove this, we'll go directly. We'll say that let A be a set then by Axiom 2 the set containing A is also a set by Axiom 3 there must be an element of the set containing A which is disjoint or contains no column elements from the set itself. So there must be an element X of A which is disjoint from the set itself. Oh, I guess I'll probably call this Y instead. This is our set X from the axiom. Since the only element of the set containing A is A itself, this means that the set A and the set containing A are disjoint, because A is the only element of the set containing A. And that means this is a direct proof then of the fact that no set is an element of itself. Because this is implying that A and the set containing A have no common elements. So this means that we cannot have the expression A is an element of itself. Expressions like this are not valid propositions. For any sets. So this resolves a piece of Russell's paradox and really kind of clarifies a little bit more what we can expect from sets. We can also use, at this point, the axioms we've written down to define the ordered pair of sets, or of elements. And we do this as follows. You see that an ordered pair is the ordered collection and that should be specific, an ordered pair of sets X and Y the ordered collection that has X as the first element and Y as the second element. You can also go on to define ordered three tuples, 4 tuples, and so on and so forth. But if you want a direct definition, this ordered pair is X comma Y can be directly defined as the set containing X and the set containing X, Y. So it's the set containing these two sets, which is distinctly different or not equal to the ordered pair YX, which is the set containing Y and the set XY. Remember, with sets, order does not matter, but if you define the ordered pair in this way, it gives you a consistent way of logically thinking of what an ordered pair is. Not only that, but with this definition of ordered pair, we can actually go about creating larger sets that are very, very important. The Cartesian product is an example of this. between sets A and B is the set of all ordered pairs with elements from each set. You denote this as A cross B. The set of all ordered pairs such that A is an element of A and B is an element of B. And this is a very, very useful tool in mathematics, one that you've probably already seen if you've taken a Calculus 4 course, or multivariable calculus course. Cartesian product between the real numbers is what we use to describe two-dimensional space, three-dimensional space. But even from like a more basic standpoint, we'll go over a basic discrete example here. If A is the set 0, 1, and B is the set ABC, the Cartesian product is a set containing 0, A, 0, B, 0, C, 1, A, 1, B, and 1, C. And it's important to note that this is different. It's not the same thing as the Cartesian product of B with A, which is the set A, 0, A, 1, B, 0, B, 1, and C, 0, C, 1, where the set of ordered pairs, where the first element coming from B and the second element coming from A, they do have the same number of elements, but these elements are directly different from one another based on the fact that the ordered pairs are different sets, or represent different sets. Sets don't care about order or listing of elements, but ordered pairs do. So if you switch the order in the ordered pair, you're getting a completely different set. Another example that's a little bit more practical in terms of applications would be if you consider a standard deck of cards. And a standard deck of cards consists of 52 cards, and each one of the cards has either a different face value and a different rank value. So the rank values are from 2 to 10. And then the rank could also be Jack, King, or Jack, Queen, King, and Ace. And the face values, there are 4 of which the heart, the diamond, the spade, and the club. The 13 different rank values and 4 different face values for any card. So if you consider the Cartesian product of the rank values with the face values, this is the set of all possible combination of rank and face. So you have 2 of hearts, you have the 2 of diamonds, you have the 2 of spades, you have the 2 of clubs, and then so on and so forth, all separate different combinations. And this gives you a 52 element set that directly describes all of the possible cards in a standard playing deck. And this is the basis of understanding, or at least beginning to understand, how set theory and why set theory is the basis for modern probability theory. In probability theory, you define what's called a sample space, and with respect to that sample space, you're looking for the probability of a certain outcome in that sample space. And I think this is a very good example showing why these manipulations that we're talking about are very, very practical and very, very important to understand. But this should serve as a good example of what the Cartesian product is doing. So moving on, we want to get into the next couple of construction axioms. And the next one is what's called the Union Set Axiom. This is Axiom 5. And I'll point out in a little bit all of the different notations that we can use for the union, but first I'll describe really what a union is. And I guess what I want to say is that the first notation that we'll see is just the union of a set X is, you put a big U right here, capital U for union, sometimes with the cup symbol next to the set X. And the reason that this is typically how we, in axiomatic set theory, write the union. We can talk about this in the next example. So if we'll say that X is the set containing 2 sets, maybe a pair set containing the set ABC and the set 0, 1, we define the union of the set X to be the set containing the elements of the sets that compose X. This is the set containing A, B, C, 0, and 1. So this kind of explains this notation right here. This is a good example. However, I don't want you to be confused. In the book, this notation really isn't touched on or used, but from an axiomatic perspective, this is the Union Set Axiom from axiomatic set theory. This is how we definitively define the union. In the book's examples, they actually really only use the notation. If you have 2 sets A and B, notation A union B is used to describe the union. And there's really no logical difference between what we're doing here and what the notation the book uses, but this example right here in the book's notation would be, say, if A is the set ABC and B is the set 0, 1, then A union B is the set containing everything in A, which is A, B, C, and everything in B, which is 0, 1. So the idea here is that this axiom really definitively uses this notation, but you can very clearly see the overlap here, and that there's really no contradiction. Both notations are perfectly fine to use. And in general, we often in mathematics see notation, various notations used for the union. So I'll kind of talk about some of the general notations. So one example would be, say, the union of all sets A that are elements of some other set X. It stands for the union of all sets A that are elements of some subset, some superset X. So this is a union of multiple sets. You can also talk about the union of index sets. So the union of all sets AI, where I is element of some beta. These are the same actual notation in some sense, but the idea here is that it's common to see statements that look like this, right? You could also have something, and this is a very specific example, if you have finitely many sets AI for I from 1 to n, say, you can write the union from I equals 1 to n of AI. You can think of this as the union of A1 with A2 with A3 and so on and so forth, all the way up to set AN. And by the end of the lecture, we'll actually see that right, you could also have, if you have infinitely many sets, countably infinite. Right, these indexing sets right here could be countably infinite. They could be uncountably infinite, which we'll get into that a little bit later on in the course, what the difference between countably infinite and uncountably infinite is. But even if you want to, say, take an infinite union, a countably infinite union of sets AI, or I from 1 to infinity, stands for the union A1 with A2 with A3 and so on and so forth, all the way up to infinity. The idea here is that we can talk about very, very complicated set unions, and it's very, very useful to do so. So the idea is that in general we can think of kind of like a pictorial representation of this. So let's do a figure here when we're talking about sets. The sets are going to be in some universe U. And if I have two sets, a set A and a set B, the union of these two sets is everything that's contained in both sets and in the intersection. So from a very basic standpoint, we can directly think of this as the logical OR operator. And this idea actually, right, leads to a totally new idea of defining set operations. So we can think of the union between two sets A and B as the set of all x in the universe that A and B are contained in, or the universal set that A and B are contained in, such that x is an element of A, or the logical OR operator, x is an element of B. And again, this is an example right here of set builder notation, and perfectly leads into what's called Axiom 6, right, which is the axiom schema of separation or restricted comprehension, where we're specifying the elements in a set by a certain, you're saying x is some element in U, in the universe U, such that some proposition is true, which is a proposition in the language of the theory that we're using. So Axiom 6, if you want to get extremely technical, is actually called the axiom schema of replacement. And really, actually what it is it's an axiom schema, which means it's not just one axiom. It's an axiom that has to be true for all formulas in the logical language of set theory. So there's actually infinitely many axioms contained inside Axiom 6. And it actually leads, the axiom schema of replacement leads to what we're going to write down here as Axiom 6, which is really all we need for this course and for the mathematics that we're going to be doing in this course. And this is called the axiom schema of separation or restricted comprehension. What this means is that given a set y in a formula in the logical language of set theory, we'll call it capital psi of x, there exists a set of z in y such that phi of z is true. This is sometimes called the truth set of whatever formula psi we're taking. So we write this set as the set of z in y such that phi of z is true, which is just the set of elements. This is called the truth set, and it's the set of elements for which some proposition is true. So the union expressed in set builder notation is really just the truth set for this statement. Likewise, right, the other examples of set builder notation we gave in at the beginning of the lecture are examples of this what's written down here as well. This is very, very neat. And what I want to emphasize here is that the axiom schema of specification here, the axiom schema of separation, can only construct subsets and does not allow the construction of entities of the more general form. Right, so I'm putting not allowed here. Not allowed is something of the form x phi of x. Right? If you don't say what set X is in, or what X is, which subsets we're taking X from, this can give you constructions that are contradictory. Russell's paradox is a great example of that. So this restriction is entirely necessary to avoid Russell's paradox. You need to only work inside subsets, or be very, very careful about where you're pulling your elements from. But this axiom really ties together, right, the stuff that we did with predicate logic to now set theory, and how we're going to be using predicate logic in set theory. And it shows that everything that we're doing is completely consistent with what we've kind of been talking about all along. So using this axiom, we can do a lot of different things. We can define new set operations, and that's probably one of the biggest things that we have. The first one we'll define as set subtraction. This is if A and B are two sets, then B minus A, which we denote or say is given by the following. This is also sometimes written as B minus A. This is the set of X in B such that X is not an element of A. And we can directly see, I guess we'll do an example. If B is the set A, B, C, D, E, F, and A is the set A, B, C, D, G, H, then B minus A is just the set E, F. It's everything that's contained in B but not contained in A. That's E and F. It's a very good example. We can also kind of like show a figure here if you want to see a diagram illustrating this. It's probably the best thing to look at. Kind of get an intuitive idea of what's going on here. You have a set A and a set B. A set B minus A is everything inside of B that's not inside of A. This directly connects to the union. We can also go through and define the complement. The complement of a set A in some universe. U is the following. We denote it by putting a C above A complement. It's really just U minus A, or the set of all X in the universe such that X is not an element of A. last operation, which is probably one of the most important operations to deal with in set theory, is called the intersection. The intersection of two sets A and B can be defined notation is an upside down cup, so kind of opposite the symbol of the union. And this is a set of X in A or B, and both A and B, A or B, such that X is an element of A, logical and X is an element of B. So the union is OR, and the intersection is AND. Right, so for example here, if A is the set A, B, C, and B is the set B, C, E, F, A intersected with B is just going to be B, C. And not only that, right, we can go through and prove that two sets are called disjoint or are disjoint. We've already defined disjoint in our other axiom. Two sets are disjoint if and only if the intersection between both the sets is equal to the empty set. So this means that they share no common elements, which is very cool. So I'm not going to prove this, but it's a relatively straightforward proof to go through and show. So for the intersection, we also have some interesting notation. Specifically, you can talk about, say, the intersection of all sets A in some reference set X. Stands for a multiple intersection, so an intersection of multiple sets. You could talk about maybe the intersection of all sets that are indexed by some index I, the index in some set B, beta. You can also even talk about, say, intersection of finitely many sets, countably finitely many sets, or countably infinitely many sets. Notation for that is the intersection from I equals 1 to n of AI, or infinity of AI. This notation right here is similar to the summation notation introduced right in a Calculus 3 course, say when you're dealing with infinite series and sequences, or just even finite series and sequences in Calculus 2 course. So this is very, very similar to that summation notation, but it's specifically for multiple intersections, and it's similar to that union notation that we introduced before. To get an idea of what the intersection is between the sets, I'll draw the following figure. You have a set A and a set B. The intersection between the two sets is this shaded region right here. This is a good example, or a good figure, kind of showing the idea of the intersection between sets and what that operation is. It's a new set that's It's all elements that's in both A and in B. So there are many properties, right, of these set operations that we've defined through Axiom 6, obey, and these properties are, in some sense, directly coming from the logical properties that we've already discussed. So the logical identities that we have already discussed, which is really, really quite incredible. So all of set theory is really coming from propositional logic, the propositional logic that we've studied already. I'm not going to list all of these, but if you, I really encourage you to look at Chapter 2, 2.22, Table 1, the table of set identities in this chapter. And you should go through and prove the identities in this, all of the identities in this table. I'll go through and show a couple of them now. I also want to point out that the book uses a slightly different notation for the complement. The book uses the notation A with an overline for the complement. That it's also used in some of the Weber problems. However, I like the C in the exponent for complements. So please just keep that in mind when you're reading through the book. But so let's go through and show some properties. We'll directly prove some properties. One of the big ones is De Morgan's law, or De Morgan's laws. And these say the following. It says that the first one the complement of A union B is equal to the intersection of A complement intersected with B complement. And likewise, you can barely see where this is going. The second De Morgan law is that the intersection of A and B, if you take the complement of that, everything not in the intersection, this is the same thing as the union of A complement with B complement. And it's no secret, right, that when we go through and actually prove this, which I'll go through and do right now, I'm just going to prove one of these right here. I'll leave the other one to you. We can directly show both of these using the De Morgan's laws just from propositional logic. And so this is going to be a proof of number one. So to prove that A union B complement is equal to A complement union B complement, we must show that this set, A union B complement, is a subset of A complement union B complement, and you have to have the reverse inclusion, or A complement union B complement should be a subset of A union B complement. Oh, and I just realized here I wrote this down wrong. This should have an intersection in it. I'm so sorry about that. Intersection, intersection, intersection. Because we define set equality in a very specific way. We say two sets are equal if each set is a subset of the other set. So in this proof, I'm only going to go through and prove part 1 here. And I'll leave part 2 to you, because it's very, very similar to part 1. So I'm going to go through and do part 1 now. So to show that this set is a subset of this set, we start by assuming that X is an element of A union B complement. So then by definition, X is not an element of A union B, and then also by definition, right, this is the negation of the statement X is an element of A union B. So we're saying that if X is in A union B complement, then by definition X is not in A union B. So this is a true proposition, which means that the negation of the statement X is an element of A union B is true. And this is where the real magic happens. The definition of A union B is directly logically defined as, if X is an A union B, that means that X is an element of A, logical or X is an element of B. And because then we have De Morgan's law, it's a logical operator law. Directly on this or right here, this is the same thing as not X is an element of A and not X is an element of B. This means that X is not an element of A and X is not an element of B. Which means that X is an element of A complement by definition, and X is an element of B complement. Which lastly means that X is an element of A complement intersected with B complement. And this finishes this first part of the proof, part 1. To finish the proof, you have to now do part 2 in a very similar manner here. However, this goes through and it completely shows you, right, how we do this. This is sometimes called, right, the forward part of the proof. This part 1 right here is the forward part of the proof, and the backwards part of the proof, right, is the other thing that we need in order to show this set equality right here between these two sets. However, this is it. This is how you go through and do this. And what's really neat here is that we've seen that all of these steps are either using set theory definitions, right, or using logical laws. And all of the things here, all the properties here in this table are the same. Going through and proving them, you use the same method. So you're going to be using basic logical rules. So De Morgan's laws really are fundamental. However, this table from the book, you're going to want to know all of the laws in the table. So this is, I'm copying it right here so that you can kind of see right, that there's a lot of them. But just like the table of logical identities that I told you back when we were learning that you should really know all of these, right? Same thing for this table right here. You should know all of these, know how to show them and justify them to yourselves. Be a good exercise to go through and prove all of these, right? But the one that we just proved was De Morgan's law. We did one of them, right, and only part of it, but you should finish this proof for practice and also go through and this is the one that we just proved. You should go through and finish the proof and then also prove a lot more of these to kind of become comfortable with doing proofs in set theory. However, right, you can see that a lot of these laws are very, very similar, if not the same, as their corresponding logical laws, and this is there's no secret here that the definition of set theory using logic is the reason for this. The reason that you have associative laws, distributive laws, you have similar complement laws, identity laws, domination laws. Right? All of these are coming directly from logic. Something that's also very important is an idea of a membership table, which we can directly kind of go over and do now. One way of proving these results is by using a membership table, just like you would use a truth table for finite sets. So a membership table, say, is that if you have, say, 3 sets right here, you can look at, say, right, is X an element of A, is X an element of B, and is X an element of C? And the idea here is in the membership table, we're kind of encoding all of the different possibilities for possible combinations of membership for each one of these sets. So B union C, right? If X is in A, X is in B, and X is in C, then X is in B union C. If X is in A, if X is in B, and if X is in C, then X is in B union C. And this is true all the way up until this possibility right here, where if X is in A, but X is not in B and not in C, then X is not in B union C. This is an example of doing a membership table, and I recommend going through and doing a number of these and looking at the examples in the book of membership tables so you can kind of get an idea of how you might do this, right, and how this is actually similar to the idea of doing truth tables.